Hmm. So we moved into chapter 6, and that's a chapter we'll spend some time on because it's really important. If you remember, I had this slide last time too, that the 3 most common chemical plant incidents are fires, explosions, and toxic releases, in that order. And by far, fires and explosions are hazardous, and when and can be very devastating. Well, they all can be, depending on the toxic release. So, this is just a repeat. You've seen this before. There are a few slides here that I added to the unit operations slide, safety slides when we had that presentation, but I feel like it doesn't hurt to see them again. But I'm going to go over them rather quickly because you have seen this already. So, fire triangle, we need fuel, oxidizer, right, and an ignition source. Those are the 3. We can't have a fire without those 3. And what to remember, of course, is that fuels can be basically anything carbon containing, but also fine metal particles, for example, are flammable. And obviously a lot of the gases. So out of those, hydrogen and acetylene are extremely flammable, and there really isn't a safe concentration of those 2. Right? If you have hydrogen and acetylene and it leaks out, you can count on you having a flammable mixture. Then you need an oxidizer, of course, and it doesn't have to be oxygen. And that's what usually gets fertilizer plants, right? What gets them in trouble? It's the ammonium nitrate. It's the nitrates that can give off oxygen. Right? And that's why it's so dangerous when a fertilizer plant is burning, because it can explode any second, basically. And then, but once you have a flammable mixture, the key is it doesn't take much to ignite it. So obviously sparks, static electricity, right? But even streaming potentials can ignite. Yes? Is there a homework posted? There should not be no. So I should have sent out an announcement, but no, I felt we haven't covered enough in chapter 6, so I decided to give you a bye week. So there's nothing due Thursday. It will be what we're covering this week will be on next week's homework. Okay, so I should have I meant to send out an announcement, but I've been sidetracked again because now my second daughter is sick. It's always something. It's always something. So I've been a little sidetracked again. But no, we didn't really have time to cover much. We saw a video last Thursday, so I felt that it's not enough to give you a homework on what we're covering today. So, and I don't want to make a homework due on a Tuesday, like a week from today, so we're just going to have it due as usual on Thursday. So, on the material, on most of the material that we're covering today, and perhaps a little bit on Thursday as well. Okay, so minimum ignition energy, that's right, the minimum, it doesn't have to be a spark though, but it's whatever energy is needed to ignite what is called an optimum concentration. And in some cases, right, the table that we have on minimum ignition energies, those are experimental values, right, where someone has been mixing things. In this case, you have a flammable mixture, an optimum mixture, in other words, and they checked how much does it take. And obviously I pointed this out before, but for acetylene and hydrogen, it's 0.02 millijoules, okay, 0.02 millijoules, so it's basically 20 microjoules. Okay, let's put that in perspective. I know you've seen this too, but it doesn't hurt to repeat. This is the minimum ignition energy for propane. It's an order of magnitude higher than that. And that's 0.25 millijoules is equivalent to the kinetic energy of a penny dropped from a height of 1 centimeter. Okay, and if you compare that, right, walking across a rug, right, when it's dry out and you shock yourself, that can be significant. That can be 2 orders of magnitude higher than that, right? And fluid flow, streaming potentials. We're gonna, if we have time, we're gonna watch a CSP video on just that. When you have filling operations, for example, you have flow of an insulating liquid, hydrocarbon liquid, right? Through metals, and even if it's bonded and grounded, you can still, you may not, if you get air into that system, you may still be safe. Okay, if we look at, this is something we didn't look at last time because we don't have too much powder in the UNINOPS lab. So if we look at the minimum ignition energies for powders, so that's in this column here. I mean, you can see that there are several orders of magnitude higher than that, as is millijoules, okay? And they're also somewhat dependent on particle size, right? I'm not sure why dust, I'm wondering if this is right. You would think that for fructose, the lower the particle size, the easier it is to ignite, and you would think that wood dust would do the same. So I don't know why larger wood particle would actually be easier to ignite. That so seems counterintuitive. But you know, between those two, right, the particle size doesn't seem to be that much difference really in micrometers. And so compared to anything else, it's on the lower side, right? So obviously sawdust, right? It's easy to see that you can have, right, that can cause fires because it's something that can easily burn. And that's what happened in China, right? They had fertilizer in that case, but it was nitrocellulose that's supposed to be wet. It's never supposed to be dry. Heat dried it up, and then that's what caused the first fire. And then, of course, it all ignited and caused severe damage. So when it comes to dust explosions, in addition to the 3, fuel, oxygen, and the ignition source, you also need to have it dispersed. That has to be dispersed and confined. And the confinement is what got Imperial Sugar. If you remember that CSP video, that's what got them in trouble because they didn't have a very good dust collection system. So sugar dust spills everywhere, right? And when they enclosed it to try to prevent contaminants in the sugar, that's when probably an overheated bearing ignited the dust because it was dispersed inside of the confinement. That small explosion just sort of rocketed through the plant. It dispersed more dust, and it was like a domino effect until there was almost nothing left of that plant. Right? And so combustible dust, or coal, sawdust. You know, some obviously even the food industry could have issues here. Sugar, flour, starch, fine metal particles. There was I think there was a small fire in mechanical engineering not too long ago, and it was because they had fine titanium particles that. So what happens is they oxidize to TiO2 and releases a lot of heat. And if you get over a certain, right, that heat can make you reach the auto ignition temperature where the surroundings have enough energy to ignite your flammable mixture. And of course, don't forget plastics. The plastics are, right, PVC, they have a lot of carbon, even if they also have halides, right? So the problem there is that when plastic burns, you can also get toxic vapor, right? So let's look at some definitions that's important, right? We're getting into this chapter. So combustion, which is, you know, I'm not sure I would put it equivalent with fire, but that's what happens in a fire. You have, you know, something is combusting. So it's a chemical reaction when a substance, whatever it is combined with O2. And that is always an exothermic reaction. and it can be highly exothermic, and that's what sometimes you will see, you know, a sawdust pile that can start smoking. And if you have something that starts in there, it releases heat when it starts oxidizing. Well, the problem is when that heat will increase the reaction rate, right? So you'll have more things oxidizing, releasing more heat, and eventually you'll have enough to actually ignite, right? And you will have a fire. Okay, we talked about ignition. So the auto ignition temperature is when the surroundings have enough energy to provide the ignition source. Flash point. That's the lowest temperature at which a liquid gives off vapor that's flammable. Okay, so in some cases, some methanol has a fairly low flash point, for example. Okay, so it's a highly flammable liquid because of that. But at this point, if that vapor is ignited, it will flash. You will have a burst of flames, but as soon as that vapor is burned out, it extinguishes itself, because there's not, the temperature isn't high enough to sustain that vapor pressure. So it burns out all the fuel in the vapor, right, in the air above the liquid, and then there's no more fuel. So that's different from the fire point. That's now a higher temperature, and at this temperature, it's high enough to sustain, right? So you will have a fire. It will not burn out by itself until the liquid fuel is gone. And obviously that's a lot of times what happens when you have a fire in a chemical plant. There really isn't a way. You have to let the fuel burn out, basically. There isn't a good way to extinguish it at that magnitude. So that's why you'll see, in some cases, it burns for days, because the fire's fighting can't do anything.
What's the difference between flash point and boiling point?
So the boiling point is just when your liquid boils and goes into vapor, right? That's when you have boiling liquid and vapor in front of it. Flash point, this is below the boiling point of the liquid. So you just have vapor pressure. Okay, everyone with me on that? So a lot of flammable liquids, unfortunately, right, have low vapor pressures. So they give off vapors that are flammable in certain mixtures. Not necessarily right away. The equilibrium at room temperature, for example, may not be flammable, right? But in this case, the liquid, this is the lowest temperature. So that's usually, right, for most things that are not highly flammable. That temperature is below the boiling point, but above room temperature, right? So you have to heat it. But as you heat it, right, you have more and more going into vapor, the vapor-gas phase equilibrium. But it's not boiling, right? But they usually have high vapor pressure, high vapor pressure, right? So, but the flash point, it will ignite, burn, and then it's done, because the temperature isn't high enough to sustain the vapor phase with fuel. And flammability limits, that might be something that you have come across. So there are only certain mixtures. And of course, the flammability limits are different from different components. Like I said, hydrogen and acetylene, the flammability limits are really it's a very large region. But there is a certain mixture, for example. So it could be too lean, which means there's not enough fuel for the mixture to burn. Okay, that's right. That's easy to see, and that's where you want to be. You want to be below that concentration, because then you can never have a flammable mixture. Right? If you're below now that's in air. So the upper and lower flammability limits are in air only. If you have pure oxygen, for example, those flammability limits will be different, and they're actually called upper and lower oxygen limits. Now the fuel mixture can also be too rich. Okay, that's so now you have, so there are a lot of hydrocarbons actually that will give off vapors that are too rich. So you can't ignite it right at the source, right? Because there's not enough oxygen for it to burn. Problem with that is what exactly? Well, what happens as the vapor cloud disperses? The concentration goes down, it mixes with air, and you are going to have a flammable mixture. The question is just how far from the source, right? And that's what happens. That just gives you a larger area for the vapor to find an ignition source. Sorry about that. I have my daughter in my office, so I promised her that I would keep an eye. If she freaks out, I might have to put a CSP video on and run out. So let's look at explosion. So the difference between the fire and explosion, like we said, there was the release, the rate of energy release. So obviously this is a rapid expansion now of gases, right? It causes a pressure wave. And a lot of the damage is due to that shock wave, right? And you can, this can be from a mechanical explosion. So it's not really a chemical reaction that causes it. You're just overpressurizing a vessel. It will still cause a burst, right, with a shock wave. Obviously, a lot of times what we're seeing are explosions, are chemical explosions. They're due to an exothermic reaction, right, which it releases a lot of heat very quickly, and obviously you might have a mechanical failure in there because the reaction vessel, but it releases way more energy than a mechanical explosion, right? And if we look at the two, we can have a deflagration or a detonation, and basically it's the difference is how the reaction front moves with respect to the pressure front. Okay, in a detonation, the reaction front, the energy from the reaction actually pushes, right, and it pushes it at a speed of sound, right. That's the limit again, which means you have a lot of pressure waves coming very closely together, and right, the faster that happens, the higher the energy release and the higher the pressure, and that's really where the damage occurs, right? So the top one is the detonation, where you have the reaction front that's actually pushing the shock front from the mechanical failure, for example. If you have a deflagration, then you see there is this pressure front is moving at the speed of sound while the reaction front is not. So the peak overpressure for a deflagration is actually lower than for a detonation. And the difference here, for example, 2 atmospheres versus 15, okay, those overpressures are huge. Okay, let's look at, we have a table in the book that lists the damage that's estimated for certain so they're all overpressures here. You see PSI gauge, or they're given it in kilopascals too. So if we start at 0.15 PSI gauge, okay, that is 1/100th of atmospheric pressure, right? So in other words, it's 14.4 plus 0.15 PSI, absolute, that you're feeling. That's where typical glass breaks, right? So it doesn't take much to break glass, right? So if you see an explosion, and that's usually all the glass breaks, right? If we go down 1 PSI gauge, okay, that's still like 1/15 of atmospheric pressure, you have partial demolition of houses. Now that was only 1 to 2. Let's keep looking here. What's 2 to 3? That's where you start moving cinder blocks. Cinder block walls, they shatter. And this one is interesting here. The limit of a crater lip, right, is 300 PSI gauge. Okay, that is, now we're talking 20 times atmospheric pressure. So you can imagine this fertilizer, can you see here's where the fertilizer